All right. Hello, my name is Muthu. I'm the current electronics lead at the Duke Robotics Club. And in this presentation, I will be describing our systems engineering efforts. Okay, so basically, there are multiple components to systems engineering that I'd like to go over. So with regards to systems engineering, the overall purpose of systems engineering is to basically provide the tools and infrastructure that allows the CS team to succeed and to be basically better, to allow them to move faster and develop code faster. So there are multiple issues that we've tackled in our systems engineering forays at the Robotics Club. So the first sort of issue that we tackled was trying to create the standard computing environment across various operating systems and architectures. For that, we use Docker, and I'll be explaining that in further detail. Next issue is maintaining similar builds and tools. Namely, we developed using ROS workspaces and developing a custom build script to abstract the low-level build details from us. The next thing I'll be talking about is our infrastructure, our continuous integration and continuous deployment systems that allow for automated builds and automated lints, which allows for the CS team to know that their code, at the very minimum, builds when they merge into master or do whatever they need to, whenever they open a pull request and whatnot. And finally, I'll be talking about our network that provides all of the connections and whatnot between the various components, like our computers and the robot computer and all of that, and the way we handle the IP address allocation and things like that. Overall, this is sort of very important in terms of industry practice, because as industry keeps on moving towards these agile and DevOps methods, this is our attempt to make to replicate that sort of style in terms of trying to solve these problems. All right, so first, let's talk about Docker and what it is, why we use it. So first of all, why do we even use it? So ROS only runs on Linux, and most students, we tend not to have Linux. Most people have Windows or Mac. This poses a problem because we can't just directly install ROS on our computers. The second problem is that even if we all did have Linux, it's not very easy to install. There are many steps to do it. You have to install their keys and install their specific things, and that takes a lot of time and takes a lot of figuring out. And finally, I guess the main concern for using Docker is dependency health. So if everyone were to use Linux, then how do we make sure that everyone has the same set of dependencies installed that works? Because if you don't have the same set of dependencies, there's always the possibility that someone's code will work, someone's wouldn't. And then there are also issues with if someone wants to install a new dependency, they now have to let every other member in the club know that you need to install this dependency. And it just becomes very painful with that, trying to communicate and do everything like that. So let me describe some of the terms in Docker and what it is. So the main sort of unit in Docker that we use is a Docker container. And so this is, as they say, an isolated and secure application platform. And it can share and access resources running either on the host or in a different container. Basically not in the container. It can access stuff outside of the container. And so these are basically the fundamental things. If you've ever heard of virtual machines, they're sort of similar to that. They're much more lighter than virtual machines. But they allow us to create an environment that is similar across everything. But how do we know that the environment's the same? So this is where the image comes into play. So the image is the read-only template with instructions for creating a container. And this is what Docker uses to actually create the container. It will, whenever you do Docker run or Docker compose run, anything like that, it's looking at the image that you stored locally. And based on that, it's creating the file system or whatever, the actual platform that we use. And so from this, you should be able to see, like, if two people use the same image, they will get the same container at the end. Not regarding the resources outside the container, everything inside will be the same. In order to actually generate these images, we have stuff called Dockerfiles. And these Dockerfiles provide the human instructions that we use to actually create the image. The image is some abstract code or I wouldn't really call it code, but just abstract stuff that we don't really understand, like how it's stored. The Dockerfile is how we actually generate this image. And then the registry is where we store Docker images. Currently, we use Docker Hub, and it's basically a cloud place where we store so that users like us, club members can all pull the same image down from the cloud. And so that's the basic terminology that we use in Docker. Just a bit more about Dockerfiles. So Dockerfiles contain actual instructions. This is a mistake. They contain instructions to build the image. And so we have multiple Dockerfiles located in this location right here. All of our Docker stuff is located in the Docker subdirectory. And so I'll show you just an example Dockerfile just to show you. So this is an example Dockerfile. It's literally called Dockerfile, as are all of our Dockerfiles. They basically just contain the steps to create the actual image, which I'll describe in further detail now. Okay. And so we use 3 different Dockerfiles, which I'll go over right now: Core, Onboard, and Landsat. I really recommend using this website to look at the various commands and trying to understand the Dockerfiles, because it's very important. Okay, so before I get into the actual Dockerfiles, how does it solve the problems that I mentioned before? So as I just stated, if 2 people have the same image, the container that they create will have the same environment. That's the entire point of the image. The container that's created from that has the same exact environment. And so the entire point of this is, so if someone adds a dependency, they can add it to the Dockerfile. And the new image that's generated from this Dockerfile will be an image that contains the added dependency. It reflects that you've added the dependency. The next part is that we can now store images in the cloud on Docker Hub. And we know that the latest version, the latest thing that is stored on Docker Hub is guaranteed to work, which I'll explain later with our CI system. But we know that if we have the latest version, that works for sure. And so if someone is missing a dependency, then if they realize, oh, we haven't pulled the Docker image recently, or something isn't working, all they have to do is they have to pull the latest image from Docker Hub. That's simply a very simple command, docker pull. And then you don't have to figure out, oh, am I missing like dependency X? Or if you're missing dependency X, it does depend on dependency Y. All that is covered with this image system, where we can just pull it from the cloud into our local place, and it's ready to run, ready to go. This also, like I mentioned before, this allows for, or maybe I didn't mention, but Docker allows for Linux to run on Windows. You can run the Linux container on Windows on a Mac, so you also get cross OS support with that route as well. So how are our images structured? So first I should mention we have to build for multiple architectures, ARM and x86. If you don't really know too much about architectures, that's fine. Just x86 is what most of our laptops have. ARM is what most mobile devices have. Like, it's what the chips actually, like how they're designed and how they use instructions. So the ARM is used mostly for the low power, that sort of systems like your phones and whatnot. And so we use an ARM system on our robot called the Jetson. x86 is more for our local development, like our laptops and everything, where we don't care about power. We need the x86 basically to run our code on the laptop. And so we have 2 main client images that people can use that they're supposed to run. And so Onboard, the name is Onboard. It runs on the robot computer, onboard the robot. The Landsat runs on our computers, the club members' computers. In a standard pool setup, you would most likely be outside of the pool with your laptop, of course. And so the Landsat is reflective of that. So our basic image structures that we currently have right now, so we have something called the base image. And so the base image, it is the base OS from one of the 2 things. If we're using ARM, then we have to use this special OS called L4T that NVIDIA gives us for their computer. They're the ones who create the Jetson, so this is specifically for them. x86 uses standard Ubuntu, Bionic Ubuntu 18.04. From this, we create a new image. The images can derive from each other. So this means that the base image will, it will inherit all of the stuff from this image and then start building on top of that. So the core image has 2 variants, ARM and x86, and it's responsible for installing stuff. I'll get into that in the future. And so the 2 client images that I mentioned, Onboard and Landsat, they both derive from this core image. And Onboard has ARM and x86 variants. Landsat only has x86. It does not have ARM because Landsat we only run on our computers, and basically everyone uses x86 on our computers. So in terms of our actual images themselves, so I should also denote before I move on, this is what denotes the dependency on images. So to get Landsat, you have to have core. To get core, you have to have base. And so like they're built on top of each other. That's the dependent network. So in terms of our actual images, so base OS, like I mentioned, L4T for ARM, Ubuntu Bionic for x86. The core image, it contains the instructions that, the Dockerfile contains the instructions to install the base ROS installation, install the dependencies that are common between both Landsat and Onboard, install them into core, and then set the password for root and allow root users to log in. Since this is the common dependencies between Landsat and Onboard, this allows us to basically reduce the code duplication and only have them in one place instead of in both Landsat and Onboard. Landsat Onboard, these two images, the two images that we use and that you probably use in, when you're testing and doing stuff, the main things it does is it sets the SSH settings, like we forward the port 2200 for Onboard, 2201 for Landsat, and then we install image-specific dependencies. For instance, for Landsat, it needs a simulator, so we install the simulator only in Landsat. We do not install it in the Onboard image. And so overall, Docker it's a very powerful tool that allows us to create this same environment between multiple computers, and that's the main reason why we use it. We have this sort of structured image layout with base, then the more important, the core, and then from that, Landsat and Onboard derive from core. They base themselves off the core, and then from that they add extra stuff that is specific to those images. And so we currently, I just want to note, we use Docker Compose for local testing. If you've done any local testing, which I hope you have, then you probably use some Docker Compose command that starts both containers simultaneously. And so it creates a local network that simulates the network we use during pool testing, and then it mounts the code inside the container. And we can use we can start the containers using a single command, which is what we do during pool testing, but it is very long and ugly, and most likely you'll have to copy paste it from the README because it's just, it's very long. And so Docker it's really helped us create the standard environment between multiple computers. That's the basis of what Docker does. All right, so next, building. What is the motive? So what is the point of building? What do I mean by building? So from our Docker stuff, we know that the dependencies exist. We know that now all the environments are the same. The dependencies exist somewhere. But now when we actually want to build the code, we need to know where they are so that our code can link with those dependencies and do whatever is necessary, can compile with them, include all the necessary stuff required to build our code. So the second thing is, as I sort of alluded to before, we have the Onboard and Landsat containers. The Onboard container runs onboard the robot. Landsat should run, the Landsat container should only run on our members, club members' laptop computers. So with regards to that, we also have two separate sets of code in our code base that run in the separate containers because the dependencies are separate. Namely, we have the Onboard stuff and the Landsat stuff. Things like joystick simulator, that's only Landsat stuff. You should never be running that in the Onboard container. Similarly, Onboard has controls, task planning, stuff like that. So how do we make sure that we're able to build those both simultaneously and all the dependencies are checked out? And so, yeah, that's the basic process of building, find dependencies, and actually create the thing that we want to create. So we use Catkin for our builds. So we have about 15 ROS packages. If you look at our directory structure, which I'll just show really quickly. So each package is one of these folders inside the source directories of each workspace, which we'll get into later. Camera view, joystick simulation, these are a few, and then we have Onboard. We have a bunch more packages here, stuff that runs onboard the robot. So the main build system that ROS uses, that it comes bundled with, is a build tool called Catkin. So Catkin is the CMake wrapper, which if you know about CMake is a way for compiling mostly C++ code, but most of our code is Python, so we don't really use it. We just use it for the Catkin little parts. that find packages and do stuff like that. And so every package will have a CMake file. It'll be known as CMake list.txt, and it'll also have a package.xml file. So this package.xml file also declares the dependencies which Catkin can consume to build the packages in the correct order. And so we abstract Catkin away with the build script that we use. Most likely, if you've built code in our workspace, you've never used Catkin, you've probably just done something like /build.sh onboard or something like that. So before I get into the build script, I want to discuss workspaces, namely Catkin workspaces that we use in our thing. So the main thing is sort of how do we, like I mentioned before, how do we separate the builds between different things that have to run? Like the package that's run on the onboard computer, we should only be building them when we're in the onboard container. We should not be building them in the Landsat container. And in fact, they will most likely fail in the Landsat container because the sufficient dependencies aren't there. All we know is that Landsat dependencies are in the Landsat container. Onboard dependencies are in the onboard container. So to do this, we use something called a ROS workspace. And so if you notice in our code base, we will have this sort of Catkin workspace thing. So if you see, we have core/Catkin workspace. This Catkin_ws, this details, this basically signifies to ROS, this is a workspace. And so we have 3 different workspaces in our repository: core, Landsat, and onboard. And you should sort of notice this, that this is very representative of our container structure. Specifically where we have the core image that's sort of related to the core workspace. We have the onboard workspace, which only runs in the onboard container, and Landsat workspace, which runs in the Landsat container, meaning it's built and you can actually execute stuff when you're in that specific container. And so that solves the problem of splitting stuff up between onboard and Landsat, making sure that they're built individually and separately, and all of that works. The core I should probably also mention this, the core workspace contains a single package, it's custom messages right now, that it contains the custom messages because we want both of these packages to have access to that. So in case we want to read the custom messages from either one of these containers, we'll be able to do that. That's why it needs to be overlaid like this, so that both of these have access, so both of them have the definitions to the custom messages. Okay, so I guess I just sort of went over this. The core workspace contains custom messages so that both containers, both workspaces will have definitions for them. Onboard is code that runs on the robot. Landsat is code that runs on our computers, our local computers, when we're doing tethered testing. Code that's not critical for the autonomous execution of the robot, things that require the tether. Okay, so in terms of building, I just want to wrap this up with, we have the build script. And so this basically simplifies the overall building of our, all of our code, since otherwise you would have to execute a long set of, I think about 6 to 8 commands to actually get everything to build successfully. And so I just want to demonstrate, I just want to show this to everyone just to make sure that everyone realizes that this is basically just a wraparound Catkin. We do the same Catkin build, but it basically just goes into the correct directory and just builds the correct packages and builds the correct thing. So it's going to go into core, build that, then it's going to go into whatever we specify, that workspace, and then build that, and then that is our overall code that has been formally built. And so it abstracts Catkin away from our users, from our members' code. So you don't have to worry about calling Catkin like 3 or 4 times on everything. And we also try to clean for easy cleaning of everything. All right, so the next part that I want to go over is infrastructure. And this is probably, to me, the most exciting part of systems engineering. This is the main difficulty in terms of infrastructure is that we have a bunch of people, we have like multiple CS subteams and electronics subteams, as well as CS members, electronics members, who all want to contribute to our code base. But how do we make sure that one team doesn't break another team's code? Like we don't want task planning to accidentally push something that breaks everyone's builds, and so now controls can't test their stuff during the pool test or something like that. We don't want anything like that to happen. because that is very painful and very irritating to fix. And then the second problem is, as I sort of maybe alluded to this before, who actually owns the Docker images? So I mentioned before that the Docker registry is where we store the cloud images, but to actually put something in the registry, someone actually has to like push the stuff to the registry. It doesn't get automatically populated, at least not by itself. So we need who actually owns it. So if say simulation adds a dependency, should they be building the image and pushing it? Or should I be building the image? Should I be pushing it? Who maintains all this stuff? That is another question that we need answering. And finally, how do we enforce good standards in our code base? Things like making sure that people use spaces instead of tabs for indents in Python, and just in general making sure that code is formatted well across the entire code base so that it's readable and understandable in general. So for this, we have our CI/CD. You might have heard this. This is a common term in the industry. It's definitely in recent years it's become very important as people move away from waterfall towards the agile structure. And so the CI stands for continuous integration, where developers are continuously integrating code and they're verifying using automated builds that run and test their code, make sure nothing breaks. And so these are smaller commits, smaller things that so that developers know that they're on the right track. They're able to push consistently. Continuous deployment is when changes to the code, they're automatically deployed to customers, to the outside world when upon a successful merge when we're ready. And so this is an industry like protocol right now. Like many large companies, like I think Amazon, they deploy nearly 25,000 times a day, or at least more than 20,000 times a day, which is that's insane. But anyways, it's really embracing the industry to move fast and move quickly. And so this is how we're trying to move fast and move quickly. So we use GitHub Actions to do all of our automated workflows. We use their GitHub Actions. They have some servers that we can use, and they have syntax and all that allow us to program and specify what stuff needs to run during our automated workflows. So our actual workflows, they're located in this .github/workflows folder that I will just show very briefly now. They're in this .github/workflows, and the workflow files are build.yaml and linter.yaml. These are the .yaml files are the ones that specify these steps and whatnot to actually execute the workflow. So we currently have, this should be linter.yaml. So we currently have two workflows, the build workflow and the lint workflow. And so a workflow it's a set of jobs. And a job is a set of multiple steps. Sort of weird, but that's sort of the classification of workflow as a single file. It's supposed to be an entire thing or entire process that has to execute, and it can do multiple things. These can conditionally execute. You might want to execute one job if something is true. If something is not true, you execute a different job. And same thing goes for steps. Each job has multiple steps that it goes through to finish that job. And everything is defined using standard YAML syntax in these .yaml files located there. And GitHub has some good references that I would recommend reading to understand what's actually going on there. But the basic, I'll go over the basic workflows that we use. So the lint workflow, super simple. Whenever someone creates a pull request or pushes to the master branch, we then lint all Python and Bash code. It's very simple. Upon this thing, GitHub has a trigger, and it will then execute. We use something called GitHub superlinter, and it will just lint through it. And if something fails, then you will see an X somewhere in the checks or located somewhere in the place. I'll just show you briefly how this stuff works just to demonstrate where stuff is. So let me just take this latest pull request. So if you see, most likely if your pull request is still open, you'll see various checks. And if you go to details for them, you'll be able to see various things. So the linter, it just linted the code base on the pull request. Pretty simple. Similar thing happened with what I'll go over next, our build workflow. But you'll be able to see, in this case, everything passed. If something failed, you would see an X, and stuff would go wrong, obviously. It should be pretty clear to see what is happening there. Okay, so the lint workflow, super simple. On pull request to push, lint all Python and Bash code. Our build workflow is a bit more complicated. So upon a pull request or a push to the master branch, we execute this job called check Docker. And this checks if anything in the Docker's directory or in the workflows directory has been modified. If it does, that means that we need to rebuild our images. If it doesn't, then we don't need to rebuild the images. We can just pull our image from the Docker Hub, from the cloud registry, and just use that when trying to build our code. So if if you haven't added any dependencies to the Docker stuff, that's perfectly fine. We just execute build without Docker, which just tries to build our code, basically, fundamentally. And it uses what's called a matrix build to do it both once for Onboard and once for Landsat. So meaning it does it once for the Onboard container, once for the Landsat container, respectively building the Onboard workspace and the Landsat workspace in those correspondingly. So if you've modified the Docker directory or the workflows directory, that means we probably do need to build the Docker images again so that we'll be able to push them later. And so that means we are going to build the Docker images. So first we try building the core image. This is again a matrix build, tries building it for x86 architecture and the ARM architecture. After this, once this successfully completes, it saves this image in a tar file, uploads it to GitHub server so that the next two stages, so the Onboard Docker and Landsat Docker execute. Onboard Docker, it's matrix build again, builds it for both x86 and ARM. And so it downloads the core Docker image that we just built, that we just saved as a tar file. It downloads it, same thing happens for Landsat, and it tries to build those images respectively using the Dockerfiles in that Docker directory that I mentioned before that you have modified in the latest thing. And so in this, if everything's successful, then we go to push Docker. This will not execute on a pull request, only on a push to master. And this push Docker pushes the images to Docker Hub. And so this basically means that whenever we push to the master branch and Docker is being modified, we're going to push the image to Docker Hub, meaning that the image in Docker Hub reflects the master branch of the Docker files in the master branch of our repository. So this is the basic overall workflow of how the Docker builds work, and without Docker, those builds also work. All right, so final remarks. So this solves all three problems that I mentioned simultaneously, this sort of infrastructure where members can't break code, since now we have to see that checks have to pass before they merge. Docker Hub reflects the Docker files in the master branch, so now we don't have to worry about who's maintaining the Docker files. If simulation does not need to push their stuff, if they make a modification, I don't need to push. It all happens via GitHub Actions automatically. So that's problem solved. And then now everything follows Type 8 standards. So all of our code is in theory supposed to be with good formatting, and readability should be simple. All right, so the final part, the network that we use in our systems. So the main question here that arises is, how do we connect our club members' computers to the robot computer during a pull test with tethered runs? Oftentimes we want to, oftentimes we don't do autonomous runs because it's difficult to control the robot. Tethered runs, we have absolute control over the robot, and we can also pull the robot back in case stuff goes badly. So how do we do that? And so the other question is how to onboard devices during autonomous runs. How to onboard devices like the cameras connect to the computer. Namely that right now, if we use a router, we don't use a router or anything on the inside of the robot. So how is that managed? Stuff like the IP address needs to be assigned to each thing that connects via Ethernet, that to each device that's connected, things like that, which it's not a big deal if you don't understand networking. This is on a bit higher level stuff, but it's fine. So very basic. So the solution is simply, so the onboard computer acts as the DHCP server. And so that means it's assigning the IP addresses to all of the various devices connected to the robot. And so this requires some one-time setup on the onboard computer, which is slightly annoying, that we do every time we purchase a new computer. And so by doing this DHCP server during an autonomous run, it can assign the IP address to the cameras and stuff, so that on the inside we can now use an Ethernet switch, which is very simple. We don't need to attach an entire router on the inside, which is takes more power, much more complex, larger things like that. So Ethernet switch is much more simple. We also assign, because of this DHCP server, the onboard computer's IP address is assigned to 192.168.1.1, which is important if you're doing pool testing. During tether tests, we connect the one port from the onboard switch to a Wi-Fi router via Ethernet. That is the tether that you may see when we do pool testing. That's large yellow cable. And then we connect our computers to the router via Wi-Fi, so that we don't have so there are only 4 Ethernet ports, and no one has Ethernet ports on their computers nowadays. And then finally, we use SSH to connect to different computers and containers. And the containers are forwarding SSH, which I mentioned previously in the Docker stuff. All right, so in conclusion, this has been systems engineering, describing creating a standard computing environment across different operating systems and architecture using Docker. I also talked about how we our builds and the tools we use, namely Catkin, ROS workspaces, and the build script. I discussed our infrastructure, our CI/CD pipelines like automated builds and automated lints and how that supports the CS team, and then our custom network that we use to ensure that everyone is connected to the robot and everything is working network-wise during runtime. And so, yes, this has been systems engineering. Thank you for listening.